Welcome to section 2.2, polynomial functions of higher degree, part 2. We're going to look at the leading coefficient test and identify multiplicity of a zero. The leading coefficient test allows you to look at the degree and the leading coefficient of the polynomial and get a general idea of what the graph looks like. So the first thing we're going to do is look at even degrees. And even degrees, you got x squared, x to the fourth, x to the sixth, and so on. Think of your x squared, that's the one you're most common with. When your degree is even, as an x squared, it either opens up or it opens down. If the leading coefficient is positive, then you know it opens up. So that's true for all even degrees. Even if the degree is higher and you have more curves, it's still going to open up. If the leading coefficient is negative, then as a quadratic or an x squared, you know it opens down, and that's true once again for all your polynomials of even degree, is that they're going to open down here. With odd degrees, you have x to the first, x to the third, x to the fifth, and so on. The one you're most familiar with is x to the first, which is your linear. So if you have a positive leading coefficient, you think of the slope of the line as positive, so that would be increasing. That same shape holds true for all your odd degrees where they have a positive leading coefficient. So even if it has more curves, you're still starting low and ending high. With the leading coefficient of negative, once again for a line that's decreasing, and once again that same shape holds true for all odd degrees with a negative leading coefficient. You'll kind of start with the y value going to infinity and then end with the y value going to negative infinity. And once again, kind of have that same shape of a line where it is decreasing or going down. So with the leading coefficient test, it gives us a general shape of all polynomials that we will be talking about. Now what I want you to think about is if I give you a graph, are you able to identify the degree as even or odd and the leading coefficient as positive or negative? So right now I want you to pause the video and answer these three questions. So now go ahead and check your answers. The first one, the degree is odd because they are going different directions. We need to know the leading coefficient is positive. You're starting at negative infinity and finishing at infinity on the y value, so that's a positive kind of slope, so your leading coefficient is positive. On the next one, the degree is even because they end in the same direction. It is positive because it's opening up. And on the third one, it is odd again, ending in opposite directions, and the leading coefficient is negative because you start at infinity and end at negative infinity on the y value. Once again, think of your slope, that would be a negative slope. So with the leading coefficient test, you can determine what the end behavior is of the graph. How is the graph ending? Now, we're not talking about what's happening in between, but what's happening as x approaches negative infinity, infinity. What is happening to that y value? And so as x approaches, f of x approaches what as x approaches negative infinity, or f of x approaches what value as x approaches infinity. And so these two answers here have to be either infinity or negative infinity because of the polynomial functions. They have no breaks in the graph there. So on example 2, there's three different examples here about using the leading coefficient test to determine the end behavior. The first thing, what does the graph look like? So you have negative 3, which is your leading coefficient, so that's negative. Your degree is odd. So if you know your leading coefficient is negative and your degree is odd, then you know the graph will look something like this. Once again, we don't care what happens in between. What happens as x approaches infinity and negative infinity? So now that we're looking at this, as x goes this way to negative infinity, what is happening to your y value? It's going to infinity. As x goes to positive infinity, where's your y value going? It's going to negative infinity. And that's what your end behavior is. So you have to write that as shown from above. So f of x approaches infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches infinity, based on that general idea of what the graph looks like. On B, the leading coefficient is positive, and the degree is even. So with a positive leading coefficient and an even degree, even though it's to the fourth, the general shape is it's going to be opening up. So as x goes to negative infinity, f of x, or g of x in this case, goes to infinity. And as x gets larger on the positive infinity side, the g of x or y value also goes to infinity. So they both go to infinity no matter whether you go to x goes to negative infinity or infinity. So g of x approaches infinity as f of x as x approaches negative infinity, and g of x approaches infinity as x approaches infinity. And on the third example here, you just have to make sure that these are in standard form, or at least you're paying attention to make sure that the highest degree is first. So this leading coefficient is negative, and the degree on this one is even. So once again, it's even, but it's negative this time, so it's going to be opening down. As x goes to negative infinity, the y value will be going to negative infinity. As x goes to infinity, the y value will also be going to negative infinity. With an even degree, they're going to be going in the same direction, so they should both be the same thing. So since this one's opening down, they'll both be negative infinity. So h of x approaches negative infinity as x approaches negative infinity, and h of x approaches negative infinity as x approaches infinity. So what I'm highlighting here is really what you're answering. You're answering the y value as x approaches negative infinity and infinity. So that is how you determine end behavior. We talked about zeros in the last video. Real zeros are the same thing. They're x values that when y is equal to 0, but since we're talking about real zeros, these will also be the x-intercepts of the graph. So we're going to find the real zeros of a function by factoring these two problems. These are two problems we did in the other video, so I'm going to go ahead and pause it and just work through them the same way I did the other day, and then we're going to talk about the repeated zeros and what they look like on a graph. So there they are, solved again. With the degree being 2, we expect to have 2 solutions, and we do. They just repeat. There's x equals 3 happens twice. On part B, we expect to have 5, and there are 5, but x equals 0 happens 3 times. So there's 3 factors of x, so that 0 happens or is repeated 3 times. So what we want to look at is what's called repeated zeros. Repeated zeros for a polynomial function are a factor of x minus a. So when a factor occurs more than once, so it occurs more than once there, it yields a what we call a repeated zero. All right, x equals a has a multiplicity of however many times that factor actually occurs. So the kind of question is, okay, so if that happens, one, we don't write that zero twice when we write our solution. But we do understand that if it is a repeated zero, something is happening on the graph, and that's what I want to talk about right now. When you have a repeated zero, and that factor occurs an odd number of times, the graph will cross the x-axis at x equals a. But when I say cross, I'm going to talk more specifically about what I mean when I say cross, because it doesn't just cross. I'm going to put another word here. I'm going to write the word bends. And I'm going to show you specifically as to what it looks like compared to when it crosses and when it actually kind of bends and almost flattens out on the x-axis there. If k is even, which you've seen this a lot with quadratics, is that it touches the x-axis, but it doesn't cross the x-axis. It only touches the x-axis with an even multiplicity. If you have an odd multiplicity at the x-axis, you'll see it kind of bend and almost level out a little bit and then continue on. So here are 2 examples from above. Example 3a is an even multiplicity. So you can see on my window here, I showed you my window picture of the graph because I zoomed in on the x-axis here. So you can see my window I changed from the standard viewing window. So you can see the graph goes down, it touches it at x equals 3, and then it goes back up. It does not cross through the graph. So that's what happens when you have an even multiplicity. With an odd multiplicity, I graphed example 3b from above, and you can see it does cross at x equals -1, and it kind of goes straight through, and then it crosses at x equals 1, and once again kind of goes straight through. But at x equals 0 with that odd multiplicity, look what happens. So it kind of, maybe I need to zoom in even a little bit more, it kind of levels out there and then continues to go on. So it doesn't just cross straight through. It kind of bends with that odd multiplicity. So that's how you tell whether it's an odd multiplicity or it's just the root only happens one time. And then at that point, it literally just crosses through. But when you see that bend there, that's when you know it's happening an odd number of times. On this last example, I'm going to take a look at all the things we talked about and then sketch a graph from what we know. So the first thing is, what is the degree? Well, the degree is 4. What we're a little bit more concerned about is that it's even. The leading coefficient in front is a 1, but once again, more what we're concerned about is that it is a positive 1. The end behavior, f of x approaches what value as x approaches infinity and negative infinity? Well, since it's an even degree and a positive leading coefficient, it's going to open up. So the end behavior will be infinity for both of those as x approaches negative infinity and infinity. The zeros, we're going to have to solve. I'll do this below the graph. So 0 is equal to, it looks like we could factor out an x squared. That'll leave us with x squared plus 4x plus 3. Then we can factor the quadratic into x plus 3 and x plus 1. And so we have two factors of x, a factor of x plus 3 and a factor of x plus 1. So we do have some multiplicity. Our solutions or our zeros will be at -3, -1, and 0. And once again, 0 has a multiplicity of 2. And so now we will sketch the graph knowing that it's going to cross the x-axis at -3, -1, and 0. And since 0 has a multiplicity of 2, it's just going to touch the x-axis at that value. So since it's an even degree and it's opening up with the positive leading coefficient, we will start here. It should go down and touch -3 on the x-axis. At some point, we don't know exactly when, it'll go back and touch at -1 and then go back, and at 0, it's only going to touch and then continue on. It's not going to cross like it does at -3 and -1 that doesn't have multiplicity, but at 0, it should touch and then go back in that positive direction of the y value. And so that is the end of the notes on the leading coefficient test, and also talking about multiplicity and what that does in terms of the graph and its factors.